Kernels are one of the most important components in convolutional neural networks. A kernel is a small matrix of numbers, and it slides over the input image or a matrix and performs convolution operations. A convolution operation is an element-wise multiplication that sums to a single value. If we look here at this example, we consider our pink values as inputs and our white values as filter values. So we look at 0.7 times 0.3 plus 0.2 times 0.1, 0.3 times 0.2, and we take a sum of all of these values. So we add all of these up after multiplying them together, which gives us 0.29. Furthermore, while primarily kernels are square, they may also be non-square, where we use non-square matrices when data has different dimensions of importance. So for example, text and images is more horizontal than vertical. Each kernel looks for specific patterns in the input, such as edges, textures, shapes, etc. And the output of applying each one of these filters is a feature map, which highlights when features appear. The values inside these kernel matrices are weights and learned during training. So if we look at a numerical example here, we have our input matrix, which is the 3 by 3 by 1, and we have our kernel, which is a 2 by 2, and we have the values within these matrices. Our output feature map is going to be a 2 by 2 matrix, where we slide this kernel over here, over our input matrix one by one. So first it goes over this white box, then it goes over this box, then this box, and this box here. So we move it to the right, and then we move it down to the left, and then to the right. And as we slide this over, we can see that, for example, we multiply our kernel values, which is 1, 2, 1, 0, with the values that we have inside this first box. So we get 1 times 1, which is this value times this value. We get 2 times 2, which is this value times this value. We get 0 times 1, which is this value times this value. And we get 3 times 0, which is this value times this value. And then we sum up these values to get 5. We do this similarly for number 2, number 3, and number 4 as we slide our kernel one by one over each of them. And for those, we get 7, 8, and 6. And then our output matrix is going to be the output feature map, which is just going to be these values. So again, for 1, it'll be when we slid it over 1. For 2, it would be for 2, etc. So we get 5, 7, 8, and 6. And the formula that we can use for this output feature map is as follows, where we take the input height minus the kernel height plus 2 times padding, which we'll talk about in a later video, divided by stride, and then we take the floor of this, which means that if we get a non-integer, we just lower it to the closest integer, and then we add 1. For the output width, we do the exact same thing, but for our input width and our kernel width. And then for the output depth, we just take the number of kernels that we have. In our example up here, we had an input height of 3, so we can consider this a 3 height and a 3 width. Our kernel height and our kernel width was 2 and 2 respectively, since we had a matrix that was 2 by 2. Our padding value we can set to 0, and our stride we can assume is also 1. If we use this formula here to calculate those, we get a 2 by 2 by 1, which is what we get in our output right here. Please consider checking us out on YouTube to see the full video.